All right, welcome back to Physical Organic Chemistry, CH8553. Hope you guys are all doing well. Today we're going to pick up Chapter 7.4, Kinetics. Now before we get into the details of the mathematics of it, let's consider a few examples as to why we worry about this and how it's useful. I'm going to start on page 384 in your textbook with the Going Deeper section. This is the graph or the figure from page 384. It's considering the reaction of an amine. Now, you're all familiar with the reactions of amines. They can be alkylated, for instance, with alkyl iodides to alkylate the amine, in this case producing a secondary amine from the primary amine. Now, this we all know is an SN2 reaction. It's bimolecular. Overall, it's unimolecular in the amine, unimolecular in the iodide, and it has a single transition state between the starting materials and the product that goes through a pseudo-trigonal bipyramidal transition state at the carbon of the leaving group. Now, let's consider what happens when the amine and the iodide are in the same compound, as it illustrated here schematically in 1. We have an alpha omega, that is a beginning and end of the molecule with an amine and an iodide. Of course, we can get a similar reaction to above, but of course it's intramolecular, where the amine reacts with the iodide at the other terminus and makes a cyclic product, illustrated by 3 here, a long path, capital Roman numeral 2. Alternatively, of course, you can have a bimolecular reaction where one molecule of I reacts with a second molecule of I in an intermolecular fashion, a long path, capital Roman numeral 1. Here, of course, producing a product that again has an amine and an iodide. Now, this, of course, can react with I again and continue to make the polymer. So this is a classic illustration of the challenges in polymer chemistry. And of course, polyamines are things like nylons, nylon 66 and so forth. Even though many of them are made by different means, this is a fundamental way of making the polymer nylon. Now the question is, how do we get selectivity? So let's first consider the kinetics of these reactions. In the intramolecular reaction, we're going to call this rate constant for that reaction Kc for cyclization. For the polymerization reaction, we're going to call the intrinsic rate constant here Kp for polymerization. Okay, now if we consider these for just a moment, we get a series of equations that we can look at. So we can write the equation for polymerization as Kp times the concentration of the starting material, I. Of course, this will be squared. If we do Kp I squared, that is of course a bimolecular reaction, and we see the second order dependence. Now for the cyclization, it'll be the intrinsic rate constant for cyclization, and since the molecule, one end of the molecule is reacting with the other, it'll have a first order dependence. Now even though this is a unimolecular reaction, we still consider it an SN2 reaction. The transition state, the stereoelectronic requirements of the mechanism, and so forth will be the same. Now, we can relate these two equations to one another, that is, the rate of polymerization or polymerization versus cyclization. Of course, in some instances, if we're trying to make a polymer, we want the polymer to be favored. If we're trying to do a cyclization to make a macromolecule, we may want the cyclization to be favored. Now, of course, this will be equal to Kp times the concentration of I squared over Kc times the concentration of I. We can do a little math here. Those cancel, and this is equal to Kp over Kc times the concentration of our species. Now, at this point, we're going to define effective molarity. Effective molarity, or EM, as being equal to the intrinsic rate constant for cyclization over the intrinsic rate constant for polymerization. And if we substitute that into the equation above, we get that this is now equal to the concentration of starting material I divided by the effective molarity. Now, these numbers for effective molarity in a typical intramolecular versus intermolecular, they're in the range of approximately 1,000 for a standard typical intramolecular reaction that's fast. That would be a 5 or a 6-membered ring. These are highly dependent upon the size of the ring that we're trying to make. So really small rings, 3 and 4-membered rings are slow, 5 and 6 are optimal, 7, 8, 9 and up, those become much more challenging. So how do we favor one reaction over the other? Well, we can look directly at the rate equations. The polymerization is a bimolecular reaction, so polymerization is favored at high concentrations. Cyclization, likewise, will be favored by dilution. And in fact, one of the best ways to do that is slow addition, so that the cyclization of the molecules in solution occur more rapidly than polymerization, keeping the concentration of your reactant as low as possible. So what exactly do we want here? We want the concentration of I to be significantly less than EM to favor cyclization. And so from this we get a quantitative insight into how we should conduct the reaction.